So in the last video, we took a look at trying to find the derivative of the sine function, and we got down to this portion right here, where if we could just find the answers to these two blue limits, we would be able to determine the final answer for the derivative of the sine function. Now, in order to find these particular limits, we're going to have to do some work, but I'm going to summarize the results here in this important theorem, and then we'll try to prove it. Notice, though, that this theorem is going to have the important starting if condition that the angle x that we're going to be using here needs to be measured in radians. If it's not measured in radians, then these limits that I'm about to write are no longer going to be valid. So here is my first limit. If I have a limit as x goes to 0 of the sine of x over x, notice that resembles exactly what's happening here in this limit, only that I'm using the variable x instead of h, which is totally fine. But I claim that this is going to have an answer of 1. Now we'll show how that works in just a moment. I'll also claim over here that if I had a limit as x goes to 0 of a cosine of x minus 1 over an x, I'll show that this is actually going to be 0. Now again, I'm just stating this right now, right? I'm just asserting it, but how do I know that that's true? Well, this is why we actually have to go and take a look at the proof. So let's take a look here at the proof of number 1. And once we've actually proved that number 1 works, proving number 2 works is actually going to be really, really easy. So let's go ahead here and note the following. We're going to say that since x is approaching 0 in the limit here on number 1, we could assume for the moment that the angle of x is the measure of, say, some acute angle, that is a small angle, an angle less than 90 degrees, maybe one like pictured here in the picture. An angle like this. Because of course if it's moving towards an angle of 0, then this angle or this kind of two sides are going to be moving towards one another, so the angle keeps getting smaller. So we can just assume that the angle for the moment is already really small and just moving towards 0 very quickly. We can use then the figure at the right over here to actually try to compute 3 different areas that are going to help us compute this limit. All right, so taking a look at the picture here, you'll see that I have a whole bunch of different points that are laid out. This is actually going to be over here a unit circle. You can see that I have a center, and over here I can kind of imagine that I have a y-axis sitting right here, and also an x-axis kind of going out right here. If this is a unit circle, then it makes sense that this point A would have the coordinates of 1, 0. I move over 1 and up 0. This point on the circle would actually be given by cosine of x sine of x, since that's how the cosine and the sine function are defined. Cosine is the x coordinates for points on the circle, and the sine is the y coordinate for points on the circle. This point over here would actually have the coordinates of 1, tangent. And it's actually fairly simple to see why that's the case by taking a look at similar triangles. I won't go ahead and actually demonstrate that here, but you could go ahead and actually see that if you were to look at this blue triangle compared to this red triangle, you could see that they are indeed similar triangles. They both have a 90-degree angle, and they both share the angle x, and so their sides are going to be in proportion to one another. And so you can go ahead and try to set up proportions to see that the side length of over here is going to be 1. That's pretty easy. But that the side length over here is actually going to be the tangent of x. Okay, well, I'm not going to go ahead, like I said, and show that here directly, but let's just assume that that actually does work. You could try to see that for yourself by taking a look at these similar triangles. But I'm going to go ahead right now and just instead focus on setting up 3 different areas here and showing how they relate to this limit. So the first thing I'm going to try to find is the area of the triangle that connects the points C, O, and A. Okay? I'm actually going to color coordinate this. Let's say that this is going to be our blue area. So again, I'm going to connect C to O all the way over to the value of A. So it's going to be this triangle right in here. Okay? Now, if I want this particular triangle area, I'm again going to use the classic area of a triangle formula. So that's going to be 1/2 whatever the length of the base is times whatever the height is. So the base of this triangle would be this horizontal distance here, which we can see very clearly is just the distance 1, since we stretch from from 0 over to A. And this has coordinates of 1, 0. Now the height of this is actually going to be given by this dashed line. That ultimately is going to be the y-coordinate of this point, which we can see is actually just sine of x. So in here, I'm just going to write down sine of x. So in total, the area for this blue triangle is 1/2 sine x. Okay, well now I'm going to take a look at a different area. This is going to be an area of a sector of a circle, and I'll color this in green. It's going to be using the same exact sides that we did for the triangle, but instead of taking this slant side here, I'm actually going to come around the edge of the circle. So notice that this green area is going to be slightly larger than the blue area for the triangle. Now I have to remember how I get the area for a sector of a circle. Really, I would be doing the area formula for a whole circle, and then just doing a certain percentage of it. So notice here that the area of the entire circle that I would have here would be represented by pi r squared. But since this is a unit circle, the radius is 1. Now I just want a percentage. I want only a slice of that circle. I want this slice. And I can use my angle to help me figure out kind of what percentage of the circle I'm using. In a total circle, I know that there would be a rotation equivalent to 2 pi radians. And so far, I'm only using x radians out of that total. So this gives me my percentage. If I simplify this up, I'll notice that 1 squared is just 1. My pi's cancel from top and bottom, and I'm going to be left with just the value of x over 2. All right, one more area. Now I'm going to find the area of another triangle, a triangle that connects the points B, O, and A. So this we'll call our red area. Okay, so this is going to connect B all the way to O, all the way over to A. So this triangle in here, notice this would produce the biggest total area. And actually, its formula for the area is very, very simple, because again, the base here is going to be 1, that stretches along the horizontal side, and the vertical height here, I can see is just going to be represented by the tangent of x. So the total area here is just 1/2 tangent x. Well, now that I have this, and I can already see that the red area is biggest, the green's in the middle, and the blue is the smallest, I can just say that we see that my blue area is less than or equal to my middle area, which is less than or equal to my big area. Technically, I don't even need the or equal to signs here, but that would be totally fine to include them. Now, I'm going to go ahead and make a quick observation. Right now, if we are saying that the value of x is approaching 0, and that x is now the measure of an acute angle, currently that would mean that I am dealing with the point up here in the first quadrant. And so I could definitely state that the sine of this, that is the y value of my point, is definitely positive. So I can say it that in the following way. I'll say since sine of x is greater than 0, when x is positive, and near 0, like it is right now, we can multiply through by 2 over the sine of x and obtain the following. So I'm going to go to this inequality right here, and I'm going to multiply everything by 2 and divide everything by the sine of x. Now, the reason I made the statement that sine was positive is to recognize here that I'm ultimately multiplying by a positive value, which means I don't have to switch the inequality signs anywhere. Notice, if I multiply this first portion by 2 and divide it by a sine, I'm just going to be left with 1. If I multiply this by 2 and divide by sine, I'm going to be left with x over the sine of x. And if I multiply this by 2 and divide by sine, notice I'm actually going to be left with a 1 over a cosine, since I can think of the tangent as really just being a sine of x over a cosine of x. So the 2 multiplied would cancel the half, and dividing by the sine would remove the sine from the top, so I'd be left with this. Now what I'm going to do is to go ahead and just quickly notice that if this is going to be true, then if I take reciprocals of all of these items here, I can actually reevaluate kind of the sizes of each of these. Think really quickly, for example, about the following relationship. Hopefully you would agree with the following just quick fact. You don't have to write this down. But hopefully you would agree that 1 is bigger than 1/2, and that 1/2 is bigger than 1/3. We agree with this, right? Now, if I was to go ahead and take the reciprocal of each of these values, like 3/1, 2/1, 1/1, and now try to recompare the sizes, what we'll notice is that the thing that used to be smallest is now biggest, and the thing that used to be biggest is now smallest. The thing that was in the middle actually stays in the middle. So I'm going to try to enact this exact same sort of a switch with what I have here. I'm going to have 1/1. I'm going to have sine of x over x in the middle, and cosine of x over 1 over here. Now, since the cosine of x was actually going to be the 1 over the cosine of x was the largest here at the beginning, it's actually now going to be able to be written as the smallest item. I'm actually then going to go ahead and actually move it so it sits over on this side. And then I can set up my inequalities like this, just so they still look like they're moving in the same direction. But cosine that used to be biggest is now smallest, and the one that used to now be smallest is now biggest. So that's kind of the idea of what we're doing here. We're just using this concept of reciprocals. Now there's a reason that we've decided to do this, and you might be able to spot the reason. We said at the very beginning that we were trying to evaluate this limit, which is a really difficult limit to work with. And long ago, back actually in section, I think it was 2.3.1, we talked about one strategy that we could use if we ever came across a limit that was really difficult to evaluate. Take a look at where sine of x over x has ended up. It's been wedged between two functions. Any idea what I could use here to maybe help try to find this limit? Well, I might be able to use the squeeze theorem. What I would have to do is to actually go ahead and think about what's going to happen with the limits of these outside pieces. So I'll go ahead and state this. I'll say that we also see that if we imagine that x is approaching 0 for the cosine of x, then this would lead us to have a limit value of 1. And if we were doing a limit as x approaches 0 of just 1, that would give me an answer of 1. And so we could say that by the squeeze theorem, we know that the limit as x approaches 0 then for the middle piece, which would be my sine of x over x, would also have to have the same limit because it's being squeezed in between. Now, technically here, since I was having x actually be approaching 0, notice here from the positive direction, this would actually be the limit as sine of x approaches 0 from the right, and so I would only be able to show this from the right. However, I can say here that a similar argument would show that the limit as x approached 0 from the left of the sine of x over x would also equal 1. And I could do that by just kind of imagining taking this picture and flipping the colored space so it would be kind of down here in quadrant number 4. So I'd be approaching 0 from below 0. And so if both the limits from the left and the right are equal to 0, we could say that then the limit as x approaches 0 from both directions is actually going to be 1. So this is great. This actually confirms that first limit that we had in the box above. And that's a lot of work to get there. If this feels a bit overwhelming and intimidating, it probably should, because this is a pretty complicated argument. But hopefully you can see that we have reached the conclusion that shows us why this first limit is indeed 1. Now we still have one more proof to do, but fortunately this one's a bit easier, and it's going to be showing that the limit of the cosine of x minus 1 over x is equal to 0. In the space that we have left, we should be able to go ahead and do this, and so I'll write out here that we're going to do a proof now for number 2. So we're going to go ahead and start with our limit as x approaches 0. Remember, it was cosine of x minus 1 over x. And I'm going to go ahead and I'm going to rewrite this just a little bit to be able to make use of the fact that we just proved. So to do this, I'm going to go ahead and actually multiply by a fancy version of the number 1. I'm going to multiply by cosine of x plus 1 over the cosine of x plus 1. Now when I do this, you'll notice that I'm creating a conjugate again, that's going to allow me to see a factored difference of squares occurring in the numerator. So when I go ahead and I actually multiply out the numerator, I'm going to end up with a cosine squared of x minus a 1. In my denominator, I'm really just going to end up with x times a cosine of x plus 1. I'm not even going to bother to distribute down there. Now, it might be the case that you notice that the top of my fraction now actually resembles another trig identity, although this one's a little bit more well known. Many of you are probably aware of the identity of the sine squared of x plus the cosine squared of x equals 1. This is actually probably the main identity that in all future math classes you should have dedicated to memory. This is very important. It shows up very often. Now what's kind of cool is that we can actually use this identity here to help kind of create this quantity or this expression. And I can do that first by just seeing that if I subtracted cosine squared to the other side, I could get 1 minus the cosine squared is equal to sine squared. Now, I don't have 1 minus cosine squared. I kind of have like negative 1 times this, right? If I multiply this right side by a negative, it would swap the sign on the 1 and the cosine and give me this. And so I could then say if I multiply the left side by negative 1 and the right side by negative 1, then I would have something that matches the top. And so if I was to put all of that in, that would give me that the numerator is the same as a negative sine squared of x over an x times a cosine of x plus 1. Now, this is still in a slightly complicated form, but actually it's really only going to be algebra and trig that are going to take this the rest of the way home. So what I'm going to do now is I'm going to see that I actually have some useful information here. I have a sine of x now in the top, actually 2 of them, right, multiplied together. And I have an x in the bottom. And I know how to calculate the limit of a sine of x over an x. So what I'm going to do is I'm going to separate my limit separate my fraction into 2 separate fractions. One of them is going to take one of the sines and the x, and the other is just going to be all the leftover stuff. So the sine of x and then the cosine of x plus 1. And since now I have limit laws that allow me to take the limit of each piece of a product, I'm going to go ahead and actually use those here. So I'll take the limit of the first fraction times the limit of my second fraction. As long as both of these limits exist, this is a valid move, and I'll be able to go ahead and simplify this all the way down. Now, fortunately, what I have here is the limit that we had established in the last part. So I know that this first portion here is just 1. Now, over on this side, I can actually just do a direct substitution because I have a nice continuous function. So I'm going to get minus sine of 0 over cosine of 0 plus 1. So this is just going to be 1 times 0 over 1 plus 1. And so ultimately, this is just going to be 1 times 0, which is 0. And I've proven that fact as well. So what we can see here is that we were actually able to justify completely what was actually going on in our box at the beginning, that this first limit is equal to 1 and the second limit is equal to 0. Now, this is obviously been a very long video thus far, but it's important to remember why we started with all of this. We were trying to find the derivative of the sine function, and we went to the definition of the derivative. We worked out some details, and we got all the way down to these two blue limits. And we said, if only I could find the value of these two blue limits, I could calculate the derivative of the sine function. And now we've gotten there. Let's go ahead and try to finish off that argument. So here's what we're going to have. Down in the box below, I state that the derivative of the sine ends up just being the cosine. And here's our proof. We know that the derivative of the sine function was able to be simplified into the following. We had a sine of x times a limit as h went to 0 of the cosine of h minus 1 over h. And this got added to a cosine of x multiplied by the limit as h goes to 0 of sine of h over h. And so, of course, if we substitute in now what we know those limits to be, we can see that this first limit evaluated to be 0, and the second limit evaluated over here to be 1. So I get a final result of 0 plus the cosine of x, which just is the cosine of x. So how about that? The derivative of the sine function actually just simplifies to be the cosine. Now, one final note before we end this video is that it's crucial to keep in mind, it is crucial to keep in mind that x here has to be measured in radians. If x were measured in degrees, this would no longer actually be the derivative formula. The derivative formula would change. And the reason that we know that is because everything in our argument thus far required that x was measured in radians. Specifically, it would change this portion of our work, where we came up with the percentage of the total circle that corresponded to the green sector. So if you change off of radians, you're going to have to change this whole part of the argument, which changes everything thereafter. But hopefully this is a nice, easy derivative rule to remember, and we'll see in example 1 in the next video a derivative for the cosine function.